This is a video for free response question number 1 from the 2018 AP Physics C Mechanics exam. A student wants to determine the value of the acceleration due to gravity g for a specific location and sets up the following experiment. A solid sphere is held vertically a distance h above a pad by an electromagnet, as shown in the figure above. The experimental equipment is designed to release the sphere when the electromagnet is turned off. A timer also starts when the electromagnet is turned off, and the timer stops when the sphere lands on the pad. While taking the first data point in part A of number 1, the student notices that the electromagnet actually releases the sphere after the timer begins. Would the value of g calculated from this one measurement be greater than, less than, or equal to the actual value of g at the student's location? The key thing to note in part A is where they say that the electromagnet releases the sphere after the timer begins. If the sphere isn't released at the correct time, and in fact it's released after the timer begins, then the amount of time it will take for the sphere, as measured by the timer, to reach the pad is actually going to be longer. And if you're measuring the time for the sphere to reach the ground to be longer, then we would perceive or calculate the acceleration as being less. So for part 1a, our answer should be that the acceleration they would calculate would be less than the actual value. And there's a couple of ways to justify this. One of them is if we look at the kinematic equation, delta x equals 1/2 at squared, where the initial velocity of the sphere is 0 because it's just being released from the electromagnet. And here delta x is represented by h, the height from the pad to where the sphere begins. So maybe I could write that as h equals 1/2 at squared. And the most important part about that equation is the relationship between the amount of time that is measured for the sphere to fall and the acceleration. And if you were to solve that equation for acceleration, what you would find is that acceleration is proportional to 1/t squared. And so if the electromagnet isn't releasing the sphere at the right time, if it's releasing the sphere too late, then we would measure a larger time. And if we're measuring a larger time, which is in the denominator in that proportionality, then we would determine g to be a smaller value or less than the actual value. The only thing I'd be careful of here is when the College Board asks you to justify your answer, you should also include some words, not just writing down equations like I have shown. But a simple one-sentence answer like, because the time is larger and because the acceleration is inversely proportional to the time for the sphere to reach the pad, then the value of g must be less than the actual value. Before part B of question number 1, there's some more information that's given. The electromagnet is replaced so that the timer begins when the sphere is released. The student varies the distance h. The student measures and records the time delta t of the fall for each particular height, resulting in the following data table. So they've corrected the mistake, and these data, the height and time data in this data table are accurate now and can be used in this experiment. So for part B, it says, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for g. And I think here in part B, we refer back to the same equation that we were using in part A. And that equation was h equals 1/2 at squared. And so we need to look at that equation and look at the variables that are being measured in this experiment, h and t, and look at the proportionality between those two variables. So I'll highlight that here. H and t squared are the things being measured in this experiment. And if we compare that to the equation of a straight line, which is the type of graph we're being asked to make, y equals mx plus b, first of all, I notice that in my kinematic equation there's no plus anything, so we should expect that the intercept of our graph will be 0. And also I see that what I should be plotting on the vertical axis, or the y-axis, is h. And what I should be plotting on the x-axis, or the horizontal axis, should be t squared. Now, if you came up with something else to plot on the vertical and horizontal axis, you might be correct, because there's a few different permutations of different things that you could plot on the graph to still yield a straight line whose slope could be used to calculate g. For example, you could flip the axes, or you could somehow incorporate the 2 on one of the axes. But for us, if I make a graph where on the vertical axis I plot the heights, and on the horizontal axis I plot the time squared, then on that type of a graph the slope will be equal to 1/2 a, or 1/2 the numerical value for g. And just after part B it says, use the remaining rows in the data table to record any quantities that I indicated that are not given in the table. And I need to include units as well. Right? So in that third row in the data table, what I should do, since the heights were already given but time squared was not given, I should calculate the time squared for each one of these trials. And so maybe I'll have in this third row delta t squared, which have units of seconds squared. And in that row I'll square each one of the numbers from the time row, and I'll get 0.011, 0.045, 0.117, 0.161, and lastly 0.203. And the reason why we're doing this is because in the next part of the question we're going to be asked to create the graph. And so when I make that graph, I'll be looking at these two columns, right? These two rows rather. The heights and the time squareds. As I stated before, here in part C we need to actually make that graph, and I've gone ahead and already done that for us. For part C it says plot the data points for the quantities indicated in part B on the graph below. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. So I've already done all of that for us. I've taken the height column from the previous slide and plotted that on the y, or vertical axis. And I've taken the time squared row from the data table and I've plotted that on the x, or horizontal axis. I have numbers that are equally spaced, intervals going up and across the graph space, and I have those 5 points there on the graph space. After drawing that, I used a ruler to create a best fit line that went through the data set. Now this is a relatively tight data set, which means all of those points are very close to the line, so there's not much variability in where you could draw that line. But I did try to make sure that maybe we had a point or two above the line, and maybe a point or two below the line, and then a couple points that the line went basically straight through. And so I think we have a good graph here. And if you're curious, all of those things that I just mentioned, like scaling the grid correctly, using the full space of the grid provided, and plotting the points correctly and drawing the line correctly, that's how you earn the points on the graph. And now in part D it says, use the straight line to calculate an experimental value for g. And if you remember from our discussion earlier in the problem, the equation we've been using is 1/2 a t squared, and as we mentioned before, the portion of that equation that the slope is equal to is the 1/2 a, because we plotted h as a function of t squared. And if that's the case, then the slope of our graph should be equal to 1/2 a. And so now what I need to do is I need to use the straight line, not the data points, in order to know the slope of that line, so that way I can find the value for g. And so what I like to instruct students to do is to completely ignore the points that are on the line. And in this case, the points in some cases lie maybe perfectly on the line, but in other cases you may have a data set that is further from the line, and it would be inappropriate to use the points themselves to calculate, even by hand, the slope of that line. So let's go through a technique where we don't use the points at all. What I would instruct you to do is to look for points where the best fit line intersects perfectly with the grid behind it. Here's what I mean by that. I'm going to go ahead and look at the grid and look for places where the blue line intersects perfectly with the grid, somewhere like maybe here. And another location where the line intersects well with the grid maybe is here. Now there are other choices that I could have made, but hopefully you can see that the grid space, which has a bunch of vertical and horizontal lines, creates a lot of intersection points, and at some locations the blue line goes diagonally through one of those intersection points. And so the rise and run that I'm interested in, which is in no way related to the data points themselves, but is only related to the line, right? In this part, they did ask me to calculate this using the line, not the data points. And so now, using those points to calculate the rise and the run, the point on the upper right, that green empty circle, has a y-coordinate of 0.92, and I found that because there are 5 lines between 0.8 and 1. So there's a spacing there of, numerically, of 0.2. So I divided that 0.2 by 5, and I found that every line I go up is adding 0.04 to that y-coordinate. So I took 0.8, and the green circle is 3 lines above that. So I added 0.04 3 times to get 0.92. So I'll go ahead and add that here so that we have a reminder of what that point is, 0.92. And then down below, it's much easier, right? It's just 0.4. So the rise between those 2 points would be the difference between those 2 numbers, which is 0.52. And now we need to do the same thing for the run. And on the horizontal axis, that's a little bit easier to do because the spacing is much more clear. Every line is 0.01 on that horizontal axis. So our first green dot on the lower left would be at 0.0678. And the other green dot on the upper right is along the horizontal axis at 0.18. And so the run between those 2 points would be the difference between those 2 numbers, which is 0.1. And so now the slope of that line would just be the rise divided by the run, which is 0.52 divided by 0.1. And that is just 5.2. So down at the bottom, the slope is equal to 5.2. And from the kinematic equation, the slope is equal to 1/2 of the acceleration measured in this experiment. So in order to actually calculate an experimental value for g, I would need to double the answer that I got for the slope. So the acceleration measured in this experiment is 10.4 meters per second squared. The only thing I would be a little bit careful of here is they actually say the word calculate in the directions for part D. So I kind of did some of my slope work, the rise and the run up above, but you might want to just show the calculations of subtracting the y coordinates and x coordinates to calculate the slope in the space provided for part D. But 10.4 meters per second squared is a pretty good experimental value for the acceleration due to gravity. And now, lastly, in part E, another student fits the data in the table to a quadratic equation. Right? The height actually is proportional to t squared, so that makes sense. The student's equation for the distance fallen, y, as a function of time t, is y equals at squared plus bt plus c, which looks like a good equation because it looks a lot like one of our kinematic equations, where a equals this, b equals this, and c equals this. So they have some numerical values for those constants in the equation. Vertically down is the positive direction. And now there are 4 different things they're asking us to do with that information. In part EI, we're asked to derive an expression for the velocity of the sphere as a function of time. Well, I happen to know that the velocity of the sphere as a function of time would be the time derivative of that position function, or dy dt. And so what is the time derivative of this equation that the student is using to fit this data set? Well, each term could be handled separately, right? The first term, using the exponent rule, would be 2at, right? The exponent of 2 would come down in front of the coefficient a, and the exponent would go from 2 to 1, so 2at plus b, and then the c would drop out, right, because there's no t dependence in that last term. So in order to calculate the velocity at any given point, you could plug in a and plug in b into this equation in order to calculate that velocity. And I think for this part, you could either leave it as it is, 2at plus b, or you could plug in the numerical values. And so quickly, I'll go ahead and do that in case that's what you wanted to do. And so 2 times a would give us 11.5 times t plus b. And b is negative 0.524, so that would be minus 0.524. So either one of those answers should be good for part EI. For part E2, it says calculate the new experimental value for G. And in order to do this, I think it's good if we understand the similarities between our kinematic equations that we use in physics and this equation that has been used to model the data set in this case. Right? The term that has the at squared, when we typically see that in a kinematic equation, right, it looks something like maybe delta y equals 1/2 at squared. The term that has t squared in it typically has 1/2 times a in front of it. And a is a constant, and 1/2 is a constant. So in this particular equation, capital letter A, that constant, represents 1/2 the acceleration. And so 1/2 the acceleration that we're looking for here, the experimental value for G, should be equal to the constant capital letter A, which is equal to 5.75. And so in order to calculate G, we would just multiply A by 2. And we happen to need to do that in part EI anyway, and it comes out to be 11.5. So the experimental value of G, the acceleration calculated using this student's equation, would be 11.5 meters per second squared. In part E3, using 9.81 as the accepted value for G, calculate the percent error for the value found in part E2. And so hopefully you're familiar with percent error calculations. The way that we find that percent error, I'll write the equation here, is the percent error is equal to, in the numerator, the accepted value minus the experimental value. And whether we have that as positive or negative is not so important, so I put the absolute value bars there. And in the denominator, we divide by the accepted value. So in the event that there is a known accepted value and an experimental value, this is how you would calculate the percent error. Of course, at the end we would need to multiply by 100 in order to make the value we get a percentage. And so in this case, I think what we go ahead and do is we plug in the numbers we have, right? The accepted value would be 9.8. The experimental value is 11.5. And in the denominator, the accepted value once again is 9.8. And then we multiply by 100. And what do we get for the percent error between those two numbers? When I perform those calculations, I get about 17%. And I think that sounds like a good answer for part E3. And lastly, in part E4, it says, assuming the sphere is at a height of 1.4 meters at t equals 0, calculate the velocity of the sphere just before it strikes the pad. To do this, I will set the position that's given in part E4, the 1.4 meters, equal to at squared plus bt plus c, right? Where a is 5.75 times t squared minus 0.524, plugging in b, times t, plus c, which is a positive 0.08. And so what I could do is I could solve this, what will be a quadratic equation, to determine the time when the sphere will be striking the pad, the time of that collision. And then I could plug in the time that I obtain into the velocity equation I wrote in part E1. So if you solve this as a quadratic, the time that you get comes out to be about 0.53 seconds. And so that time is equal to 0.53 seconds. And the equation for the velocity of this sphere as a function of time is equal to 11.5 t minus 0.524. And so I can plug in 0.53 seconds into that velocity equation to obtain the velocity right when it's going to strike the pad. And when I calculate that velocity, it comes out to be about 5.5 meters per second.